behavior of electrons. So de Broglie proposed in 1924 that particles can have wave-like character in addition to their particle character. So we can observe the wave nature of an electron by looking at electron diffraction. We get interference patterns, and what is very disturbing to me is that those interference patterns are not caused by pairs of electrons interfering with each other, but single electrons interfering with themselves. So if we send electrons toward this barrier with two slits, just like the one in the box on the beach, right? Waves going through these two slits create a diffraction pattern, this interference pattern. So only waves can do this, particles can't do this. So this is proof that electrons are waves, because we get the same interference pattern that we see with light waves. Any questions? So, an electron interfering with itself, how's that possible? Well, if the electron is a wave, then it becomes a little easier to think about. If the electrons were behaving just as particles, when we did this experiment, we would just see two bright lines. Because particles, they're just going to be going in a straight line, and so if they happen to hit this, then they're going to go through and they're going to hit the screen over here and make a line. But that's not what we see. We see the interference pattern. So electrons are waves. So that wave nature is an inherent property of individual electrons. And de Broglie predicted the wavelength of a particle was inversely proportional to its velocity. So this is known as the de Broglie relation. I'm not sure why it's not called an equation, but so lambda equals h over m nu. No, mv. Sorry. You see all these guys down here? Can you really tell the difference between them? So in this one, we've got Planck's constant again. There's Planck's constant. This is the mass of the electron, and this is the velocity of the electron in meters per second. And then this wavelength would be in meters. So we can use that to calculate velocities. So what's the velocity of an electron? Okay, shut the door so we can't hear the guy talking on the phone in the hallway. What's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10 meters. So they're giving us a number here, and they're saying that this is about what the wavelength is. They're kind of saying it in a roundabout way, right? The velocity of an electron that has a wavelength that's about the same length as a chemical bond. Why that might be interesting is another topic. What are we trying to find? We're trying to find the velocity. Okay, so we're going to use the de Broglie relation. The lambda, the wavelength, is equal to h over mv. Oh, I thought maybe I had the mass of an electron there. Hey Siri, what's the mass of an electron?
Here's an answer from Windows2Universe.org. An electron has a mass of 9.11 x 10 to 28 grams.
Yeah, she says 10 to 28 grams. It's 10 to the negative 28th power. Okay. So that's the mass of an electron in grams. We've got the wavelength is 1.2, gosh, that doesn't look very good. 1.2 times 10 to the minus 10 meters. And then we also can find out what Planck's constant is, 6.626 times 10 to the minus 34 joule seconds. You don't need to memorize that. I barely remember it when we're actually doing this chapter. So we are trying to find the velocity. Here we have an equation with a fraction in it, and fractions cause people lots of trouble. So let's cross multiply to get rid of the fraction. So that's going to give us lambda lambda times the mass times the velocity is going to equal h. And we're trying to isolate the velocity. So now we're going to divide both sides by lambda m. And we're going to end up with the velocity is equal to Planck's constant divided by the wavelength times the mass. There's other ways to think about doing this. So when I asked Siri, she gave me this mass in grams. But when we're dealing with joules and wanting things to cancel out, we need to use kilograms. So we need this to be in kilograms, and that's what the book gives it to you in. It's 10 to the minus 31 kilograms. Okay, so we've got 6.626 times 10 to the minus 34 joule seconds divided by 1.2 times 10 to the minus 10 meters. Yeah, that's just got no chance of fitting in there. And the mass, 9.11 times 10 to the minus 31 kilograms. Did not plan the use of my space very wisely. 6.626 EE negative 34 divided by, open parentheses, 1.2 EE negative 10 times 9.11 EE negative 31, close parentheses. And my calculator is giving me that 6061105. Wow. How many significant figures should that number have? 2, because this wavelength only had 2. Okay. Now, what's the unit on that? So here we've got joule, which is a kilogram meters squared per second squared, times seconds, and down below we have meters times kilograms. So the kilograms cancel. This meter cancels one of those meters. This second cancels one of those seconds. And our unit ends up being meters per second. I don't expect you to be able to do that. I just want to show it to you so that you know I'm not just, pulling tricks on you. This is a number that should be recorded in scientific notation. Especially since, some students might want to tell me it's 61 meters per second. Okay. So I'm going to move the decimal point. Let's do a different color. That might be helpful. I want the decimal point to be over there, right? So I'm moving it 1, 2, 3, 4, 5, 6 places. So I've got 6 point. I'm keeping this 0 place, but the next number is 5 or greater, so this rounds up to a 1, times 10 to the minus, what did I say, 6? Meters per second. Is that a positive 6 or a negative 6? Positive 6. Because how would you feel about that for a paycheck? That'd be great, right? Awesome. I'd feel very positive about it, right? There you go. That's the velocity of the electron. Any questions? Yeah. How come we had to convert to kilograms? That's a great question. So, in the metric or the SI system, there are base units and then there are derived units. So energy is a derived unit, and it's mass times acceleration. Acceleration is also a derived unit, and it's meters squared per second squared. The kilogram is the base unit, and so that's the mass unit that shows up in all of these things. Meter and second are the other ones. Yeah, great question. If I was giving that to you on an exam, either in the problem or on the useful information sheet, I'd give you the mass in kilograms. Siri was just messing with me. Yeah, you heard me, didn't you? Just make sure we don't miss, don't want to miss anything. Okay. Since quantum mechanical theory is universal, it applies to all objects, regardless of size. Therefore, according to the de Broglie relation, a thrown baseball should also exhibit wave properties. Why don't we observe such properties, say at the ballpark when a ball is thrown? It doesn't look like a wave, does it? So, why can't we see it? Choice A, because of the baseball's large mass, its de Broglie wavelength is minuscule and insignificant compared to the baseball size. Or B, since baseballs do not have any charge, quantum mechanics does not apply to them. Or C, quantum mechanics does not apply to baseballs. Yeah, somebody chuckled. Well, up here it says quantum mechanical theory is universal, it applies to all objects. Okay, so, it's this one. We can't see its wavelength because its mass is so big that the wavelength is just almost zero, right? So you can't see that it's moving as a wave. It just is so little it doesn't matter. But in theory, it does have a wavelength. Any questions? The uncertainty principle. Okay, so we talked about electrons having a wave nature and also a particle nature. When you try to observe the wave nature of the electron, you cannot observe its particle nature. When you observe its particle nature, you cannot observe its wave nature. So the wave and particle nature of the electrons are complementary properties. The more you know about one of them, the less you know about the other. It's kind of like just this unsolvable thing, right? So any experiment where we're designed to observe the electron will detect the electron and will observe it as a particle. So this is that same setup that gave the interference pattern, but now putting a laser beam here allows the experimenter to observe the electron as a particle. As a particle, it has to go through this slit or through that slit. So here, observing it as a particle, we get two lines here. You take this laser away so that you can't observe it being a particle, and now it behaves like a wave. How does it know you're observing it? Right? I don't know. there's some just really mysterious things in this chapter. Well, Heisenberg came up with an equation. It's kind of a messy equation, but this is what it is. And I think there's a question or two about this in a worksheet, but that's not a good exam question. What it says is that the uncertainty in the x position, or uncertainty in the position of the electron, times the mass times the uncertainty in the velocity is greater than or equal to h over 4 pi. So this is a constant, right? So if we get delta x to be really small, then delta v is going to be really big. If delta v is small, delta x is big. You can't simultaneously measure the position and the velocity of an electron. You can measure the velocity if you have no idea where it is. You can measure its position if you have no idea how fast it's moving. Isn't that disturbing? Electrons are just squirrely little buggers. Any questions about that? It's like, I think I have a whole bunch of questions, but I can't actually put them into words, right? This is one of those kind of things. Okay, which statement best summarizes the uncertainty principle? Both the position and the velocity of an electron can be accurately known at the same instant. Either the position or the velocity of an electron can be accurately known at the same instant, or neither the position nor the velocity of an electron can be known at the same instant. So what the uncertainty principle says is the more you know about one, the less you know about the other. It's not saying that you can't know the velocity at all. It's saying if you know the velocity, then you can't know where it is. So the correct answer is B. You can know one or the other, but not both at the same time. Any questions about that? So, classical Newtonian physics, particles move in a path that's determined by their position, their velocity, the forces acting on it. You know, you throw a baseball and you can predict where it'll land. I mean, have you ever watched a professional baseball game and you see that outfielder and this ball and, you know, he doesn't have a calculator or anything, but his brain is a calculator. And without recognizing what he's doing, he is calculating the trajectory of that ball and moving his body so he gets right under it to catch the ball. Right? It's really amazing. But you could calculate all those things and predict where the ball's going to land. That's called determinacy. The present determines the future. Well, since we can't know the position and the velocity of an electron at the same time, we can't predict the path that it will follow. So that's called indeterminacy. We can only describe what's going to happen in the future statistically. We can't say it's going to do this. We can say, well, there's this probability that an electron will be found in this region. Does that mean it's going to actually be in the region? No, it could be over there instead. But maybe 90% of the time it would be found here. So that's the best we can do. So here's that baseball. I get ahead of myself a lot. So the ball's hit, it has a trajectory. We've got the force of gravity pulling on the ball. There's some factors of air resistance as the ball goes through the air. And we get the velocity, and you can predict where it's going to land. So if we're looking at the pitcher pitching the ball, we can predict where the ball is going to go, right? You know, a good pitcher can throw exactly the same pitch over and over and over again. Or think about, you know, getting a pitching machine, right? You stick the balls in the pitching machine, and it goes the same speed, the same place every time. If you did that with electrons, instead of all of them hitting in the same place, they would be scattered around. And there would be a 20% chance that it would hit in this smallest region, 40% in this area, 70% chance that it would land in this area. But it could come up and hit this woman right between the eyes. It could, hit the batter's knee. That's not out of the realm of possibility. So we can't say where the electron's going to go. We can say it's probably going in this area, but we can't say where it actually is. It's very bothersome.